Welcome to this custom-tailored deep dive. We are so glad you're here with us today because we're starting with a premise that, honestly, well, it kind of broke my brain a little bit when I first read it.
Oh, yeah, it's definitely a brain breaker.
Right. Because, think about the AI you interact with every day. You type in a prompt, it understands your language, it writes an email, or maybe it summarizes some dense document for a meeting. We're just completely used to AI mastering human language.
Yeah, that's just the baseline now.
Exactly. But what if AI didn't just understand the words we type? What if it actually understood the fundamental physical laws of nature?
I mean, it represents a massive conceptual leap. We're
Mhm.
talking about moving from an intelligence that, you know, parses syntax and grammar to an intelligence that fundamentally intuits how the physical universe actually operates.
Which is wild.
Huh.
So, we're drawing on some fascinating insights today from an article by enterprise architect and applied AI leader Deborah Pruseth. And it's called AI Fluid Dynamics Simulation Predicting Convection with Walrus.
A bit of a mouthful, but the content is incredible.
It really is. And our mission for you today is to explore how this specific application of AI is fundamentally changing scientific computing. We're talking about moving us away from these agonizingly slow, incredibly complex physics calculations and toward lightning fast predictions.
Which honestly has implications for quite literally everything we build.
Uh,
I mean, the physical world is entirely governed by fluid dynamics. Air behaves as a fluid, water behaves as a fluid.
right, it's everywhere.
Exactly. And for decades, our ability to engineer better vehicles, better medical devices, energy systems, all of it has been hard capped by the sheer speed of our calculations.
Okay, let's unpack this because to really appreciate the solution here, we have to deeply understand the problem that traditional engineers are facing right now. And I promised you we wouldn't turn this into some overwhelming heavy math lecture, but we do need to look at this massive technological bottleneck.
Yeah, we have to set the stage.
So let's talk about traditional computational fluid dynamics, or CFD as they call it. Here is how I was kind of picturing it as I was reading through the source material. Imagine like you're standing on the bank of a rushing river, and your job is to predict exactly how the water is going to flow around a bend in the river up ahead.
Okay, I like this.
The traditional way of doing this would be trying to calculate the exact movement of every single drop of water. You're factoring in how each drop collides with every other drop, how it deflects off every single, microscopic jagged edge of a rock, and how the underlying current pushes it along at every single millisecond.
Right.
And it is incredibly undeniably accurate, but it sounds completely exhausting.
Well, it is exhausting. It's exhausting for the people running the simulations, and it's just overwhelmingly exhausting for the supercomputers doing the actual math.
Yeah, I bet.
Your river analogy captures the core issue beautifully, actually, because what you're describing there is the attempt to mathematically map reality perfectly. And in the world of fluid dynamics, the gold standard for that perfect mapping is a set of math called the Navier-Stokes equations.
Right. I remember the author bringing up the Navier-Stokes equations, which, sounds deeply intimidating.
It does sound scary.
Yeah, but from what I gather, the math itself isn't broken or flawed, right? It's just entirely too heavy for computers to carry efficiently.
Exactly. What's fascinating here is that the Navier-Stokes equations are brilliant. They perfectly describe fluid motion by tracking how velocity, pressure, temperature, and density all interact at this microscopic level.
Okay, so it works.
It works perfectly in theory. But to solve a real-world engineering problem using these equations, you have to break down your physical space, say the air around an airplane wing, into a three-dimensional grid made up of millions of tiny little cubes.
Millions of them.
Millions. Then the computer has to solve these insanely complex equations for every single one of those millions of cubes. And it has to do that over and over again for every fraction of a second of time you want to simulate.
So if I want to simulate just 1 single second of water flowing over a rock or air flowing over a wing, I'm forcing a computer to do millions upon millions of microscopic calculations.
Exactly, and that massive volume of calculations is why Pruseth points out that solving these equations takes minutes, hours, or even days for just a single problem.
Wow. Days.
Yeah, the computational expense is astronomical. And as our designs get more sophisticated, the grids have to get smaller and more detailed. I mean, a coarse grid might miss the tiny eddy of wind that causes drag on a wing, so engineers constantly demand finer grids.
Bringing this into the real world, the article gives this fantastic example of designing a new commercial aircraft wing. Because obviously an airplane wing doesn't exist in a vacuum, right?
No, it lives in a complex fluid environment because Well, the atmosphere basically acts as a fluid.
Right. So before an aerospace company even thinks about manufacturing a physical prototype or putting it in a real wind tunnel, their engineers have to simulate thousands of different airflow
Oh, well,
conditions.
absolutely thousands.
They're testing different cruising speeds, different altitudes with thinner air, different angles of attack during takeoff, chaotic weather conditions. It's a lot.
And for every single one of those thousands of conditions, a supercomputer is sitting there churning through millions of Navier-Stokes equations.
Just grinding away.
Grinding. You end up in a situation where the engineering, the creativity, the whole discovery process is literally waiting on the math to finish. The source explicitly notes that as these simulations become larger, the computation costs grow so rapidly that they basically become a wall.
And because these mathematical equations have become this massive, unavoidable bottleneck in design, scientists looked at the problem and realized that, building a slightly faster supercomputer just wasn't going to fix it.
Right? You can't just throw more hardware at it forever.
Exactly. We didn't need a faster calculator. We needed a system that could just learn the answers without doing the math from scratch every single time a gust of wind changes direction.
Which requires completely rethinking what a simulation actually is.
Mhm.
I mean, we're shifting from deterministic calculation to pattern recognition.
Yes. And that brings us to the major aha moment of the source material. Instead of painfully solving the Navier-Stokes equations for every single microscopic grid point, what if an AI could just look at past fluid states, look at future fluid states, and just learn the relationship between them?
It's such a brilliant pivot.
And this is where we're introduced to Walrus. So Walrus is a physics foundation model developed by a group called Polymathic AI. And, when most of us hear the term foundation model today, we immediately think of large language models.
Right, like ChatGPT.
Yeah, we think of AI trained on the entire internet of text, predicting the next word in a sentence.
But Walrus is not trained on text at all. It was trained on thousands of actual fluid simulations.
Which is wild to think about.
It is. The AI looks at physical space as a massive grid of data points, tracking pressure, velocity, geometry, and learns the rules of how those numbers push against each other.
This is where the source used an analogy that really clicked for me, and I want to highlight it for you listening. Think about how ChatGPT works. It doesn't actually know grammar rules in the traditional sense of a textbook, right?
No, not at all.
It just looks at the words you've typed, relies on the massive patterns it learned during training, and predicts the most logical next word.
Exactly.
Well, Walrus is doing the exact same thing, but with physics. Just like ChatGPT predicts the next word in a sentence, Walrus predicts the next physical state of a fluid.
Yeah, its entire goal, as the author states, is profoundly simple: predict the next state of a fluid given its current state.
It's just predicting the next frame.
Right. It represents the fluid as a geometric mesh, looks at the numerical values of the fluid on that mesh, and predicts the next set of numbers in the sequence.
Okay, I do have to push back here for a second, though, because this is where my brain got stuck while reading the material.
Okay, hit me.
If it's just predicting the next frame based on patterns, isn't it technically skipping the actual physics? I mean, if I'm designing a commercial airliner that hundreds of people are going to fly on, I want the engineers to have done the actual math.
You want the receipts.
Right. I want the Navier-Stokes equations solved and verified. If Walrus is just acting like a glorified weather forecast, guessing the next state based on historical patterns, how can we possibly trust it for critical engineering?
That is the essential question. And it's a very natural hesitation because we are so conditioned to believe that deterministic math is the exclusive path to physical truth.
Right. Math is math. It's absolute.
But the core takeaway from the source addresses your concern directly. Physics and machine learning are not competing here. They complement each other. Walrus isn't just randomly guessing. It's learning the underlying dynamics directly from the data.
But it's doing that without writing out the equations.
Without explicitly solving the equations at runtime, yes. But remember, the training data itself, those thousands of fluid simulations it studied, were generated by those exact physics.
Oh, I see.
The AI has internalized the rules of Navier-Stokes without needing the formula written out for it every single time. By studying how fluids have behaved in thousands of extremely complex scenarios like smoke, water, compressed air, It has recognized the unbreakable geometric patterns of how physical matter interacts.
So it's like a master chess player who doesn't need to calculate every single possible move on the board to the end of the game because they've just seen the pattern of the pieces a million times.
That is a great way to put it.
They just intuitively know where the pressure is and where the attack is coming from.
Exactly. The intuition is built on a foundation of absolute physical reality. And the result of this data-driven modeling is just staggering.
How much faster is it, actually?
Well, by shortcutting the need to repeatedly solve those expensive numerical equations, Walrus turns something that would normally take days of computational prediction into a process that takes mere milliseconds.
Days of computation down to milliseconds.
Milliseconds. And it achieves this while maintaining impressive accuracy.
It is genuinely hard to even wrap your head around that level of acceleration. I mean, days to milliseconds.
And if we connect this to the bigger picture, think about what that does to the iteration cycle of an engineer. If you have to wait 3 days to see if your new wing design works, you might only test, what, a dozen variations a month?
Right. It's so slow.
But if you can get an impressively accurate prediction in milliseconds, you can test 1,000 variations before lunch. The speed of discovery just goes vertical.
Okay, but if we can simulate 1,000 wing designs before lunch, who actually gets to do that? Because my first thought when I hear physics foundation model trained on thousands of simulations is that you'd still need like an MIT basement and $1 billion supercomputer cluster just to turn this model on.
Well, historically, that would have been the reality for anything involving advanced computational fluid dynamics.
Right. But the author, Debabrata Pruseth, completely shatters that assumption here. And this is so cool. This isn't just a theoretical white paper. The source material is quite literally a hands-on tutorial.
Yeah, he walks you right through it.
He provides a guide that shows you how to run this Walrus model in Google Colab. You don't need to buy a massive server farm. Google Colab is basically a free digital scratchpad that runs right in your web browser. It allows anyone to write and execute code on cloud servers.
Which speaks to a massive trend we're seeing right now, the democratization of science. Pre-trained scientific models are making advanced research accessible to beginners, to students, and to independent researchers who just do not have access to institutional computing power.
I want to walk through the workflow that Pruseth outlines because it is unexpectedly straightforward. So first, you load the pre-trained Walrus model. The heavy lifting of the training, the millions of dollars of computational power required to teach the AI physics that's already done.
Right, you're just downloading the finished brain.
Exactly. Second, you download the sample simulation data. This is essentially setting up your initial conditions. You're telling the model, here's the shape of the space, and here's how the fluid is moving at second 0. It's like dropping a virtual drop of dye into a virtual stream.
Perfect analogy.
Then third, you run the inference, which is just asking the AI to predict what happens at second 1, second 2, and so on. And fourth, you visualize the predicted flow fields and compare them against the mathematical ground truth.
It is conceptually identical to downloading a pre-trained image generator and asking it to draw a picture. Except here, you're asking it to accurately simulate physical convection based on numerical starting points.
And in the article, the author actively encourages the reader to experiment. He gives a list of things to try once you get the digital scratchpad working.
Yeah, you really have to play with it.
And one of his specific suggestions was to increase the prediction horizon, meaning ask the AI to predict further and further into the future. That made me wonder if we're relying on an AI to predict the next physical state, and then predicting the state after that based on the first prediction, don't the errors snowball?
Ah, yes.
It sounds like a photocopy of a photocopy,
Yeah.
like a bad weather forecast where day 1 is highly accurate, but by day 7 it's completely wrong because tiny mathematical errors just compounded on top of each other.
That is incredibly perceptive, and it's exactly why the author emphasizes those specific experiments. In any autoregressive model, which is a model that feeds its own predictions back into itself as the new starting point errors, will inevitably compound over time.
Right, it's unavoidable.
It's a known challenge in scientific AI. The simulation might be perfectly accurate for the first few milliseconds, but as you extend that prediction horizon, the slight deviations from traditional Navier-Stokes math will absolutely begin to accumulate.
Which means you absolutely have to know the model's limits before you rely on it.
Precisely. Pruseth highlights the importance of not just running the model blindly, but actively measuring inference speed, and crucially, visualizing the prediction error. You have to compare the AI's prediction against the mathematical ground truth to understand exactly where the model's intuition begins to break down.
That makes a lot of sense.
He also suggests experimenting with different initial conditions. As the source notes, this is where real learning happens. You have to poke the model, give a chaotic initial state, and see how well it maintains physical fidelity under pressure.
And because these tools are highly accessible, I mean, running right in a browser and unbelievably fast, they aren't just sitting in coding tutorials. This isn't just an academic exercise for computer science students. This data-driven approach is actively disrupting major industries as we speak.
Oh, the foundation is expanding rapidly. The article makes a point to zoom out from just Walrus and fluid dynamics. Scientific AI is becoming one of the fastest growing areas of machine learning, period.
It really is everywhere.
Researchers are taking this exact same philosophy, skip the agonizing math, learn the physical patterns from massive data sets, and applying it everywhere.
Yeah, the source lists foundation models being built for global weather prediction, highly complex climate modeling, molecular simulations for new drugs, material discovery, and even protein folding.
Right.
All of these are fields that have historically been just choked by the sheer computational cost of perfect math.
Let's focus on the specific real-world applications where AI-based fluid prediction is already making an impact today, because the list Prusith provides is pretty extensive. We already discussed aerospace design, instantly simulating airflow over wings, but there's also automotive aerodynamics.
That is such a perfect visualization for this. Imagine a car designer working on the aerodynamics of a new electric vehicle. In the past, they'd design a new bumper, send it off to the supercomputer, and wait days to find out if it actually reduced air resistance to increase the EV's battery range.
A painfully slow feedback loop.
Right. But now, picture that same designer reshaping the bumper in a 3D modeling program and watching the air resistance metrics update in real time on their screen like a video game.
Wow.
The AI simply knows how the air will behave around the new curve instantly.
That's incredible. And weather forecasting and renewable energy optimization are also fundamentally just fluid dynamics problems on a planetary scale. Imagine optimizing how wind flows through a massive offshore turbine farm to maximize power generation.
Oh, that's huge.
Yeah, you could be adjusting the angles of the blade second by second based on instant AI predictions.
The list gets even more intimate, too, and this is where the stakes get incredibly high. Medical blood flow analysis. Because, blood is a fluid and it obeys fluid dynamics.
Yeah, absolutely, Doc.
Think about a patient who comes in needing a stent. If a doctor wants to understand exactly how inserting a tiny metal tube is going to change the blood flow pressure in that specific patient's uniquely shaped artery, they cannot wait 3 days for a supercomputer to solve Navier-Stokes equations.
The patient doesn't have days.
Exactly. They need that prediction instantly to make a surgical decision. AI fluid dynamics makes that life-saving speed possible.
We are also seeing heavy adoption in robotics, which relies entirely on real-time physics calculations to interact with the chaotic physical world. If a robot is pouring a liquid or navigating through a dense fluid, it needs to understand the physical reaction of that environment instantaneously.
It basically takes the creative problem-solving phase of engineering in all these fields and entirely removes the speed limit.
It really does. If we connect this to the bigger picture, what we are witnessing is the dawn of a new engineering methodology. As these models continue improving, engineers are not going to throw away traditional physics.
Yeah, of course not.
Instead, as the author states, they will increasingly combine traditional physics with AI to radically accelerate design and discovery.
So it's a hybrid future. You use an AI model like Walrus to instantly brainstorm and test 10,000 wild conceptual designs. You find the 3 that show the absolute most promise, and then, and only then, you run the expensive, traditional, time-consuming mathematical equations on those 3 final candidates.
Exactly. It allows human intuition and AI intuition to work in tandem. You get the explosive creativity and speed of pattern recognition validated by traditional math only at the very end when absolute precision and safety tolerances are required.
Man, that is powerful. So as we wrap up this deep dive, let's pull all these threads together for you. What we've learned from Prusith's insights is that AI is fundamentally transforming scientific computing. Foundation models are no longer limited to generating text or drawing pictures. They are actively mastering the physical world.
They're stepping off the screen and into reality.
Exactly. By adopting this data-driven approach where AI learns the underlying geometry and dynamics directly from historical data, we are successfully turning what used to take days of agonizing computation into mere milliseconds of highly accurate prediction.
Physics and machine learning are proving to be truly complementary forces here. And perhaps most importantly, pre-trained scientific models are taking these incredible capabilities out of institutional basements and making advanced research accessible to anyone with an internet connection and a curiosity to learn.
Which brings me right back to where we started today. We opened by marveling at an AI that doesn't just understand language, but actually understands the intricate physical dance of how a fluid moves.
Like,
And I want to leave you with this thought to mull over as you go about your day. If an AI system like Walrus can successfully learn the incredibly complex, chaotic dynamics of how fluids move just by observing historical data, without ever being explicitly taught the underlying Navier-Stokes equations, what other fundamental, unbreakable laws of nature might AI soon be able to intuit just by watching the universe happen?
that is a deeply fascinating question. The universe is full of patterns, just waiting to be recognized.
It really is. Thank you so much for joining us on this deep dive. Keep questioning, keep experimenting, and we really encourage you to go find that tutorial and see the physics happen for yourself.